Welcome everyone to today's webinar. Today's Veolia Water Tech Talk is about the advanced biological aerated filter technology and how to meet stringent TSS, COD, and nutrient limits. Again, my name is TJ Willits with Veolia Water Technologies, and I'll be your moderator for today's event. Now we just have some housekeeping items to go through, so if you could advance that slide. Everyone should be hearing me speak now. Everyone's microphone is muted at this time. There are two methods to listen to today's presentation. The first one is to listen through your headphones or speakers. And if you have issues with that, there's an alternative, and you can go ahead and click on the alternative phone call method, and it'll give you a phone number to dial in and listen to the presentation. Now, the webinar is being recorded right now, and you'll be sent a copy of that recording to watch on demand about a day or so after the presentation. Now, though everyone's mics are muted, we want to make this presentation as interactive as possible. We reserved a little bit of time at the end of the presentation for some Q&A. So if you have a question at any time throughout the presentation, just go ahead and enter it. On the right-hand side, you'll see a question panel, and we'll try to get to as many questions as possible at the end of the presentation. Now, today's Veolia Water Tech Talk is just one of many that we offer. Though we're near the end of the year here, we do have several on-demand webinars available at our website, veoliawatertechtalk.com. So if you head over to our website, you'll find a button and you can go and watch any of those on-demand webinars at your leisure. And for those looking to have some continuing education credits, we do offer a PDF participation certificate. And again, that'll be sent out in the follow-up email tomorrow, and you'll have that in your inbox. So be on the lookout for that PDF certificate. And something that's a little fun, we really value your feedback. And if you take a survey at the end of today's presentation, it takes about 30 seconds, 60 seconds. We'll go ahead and enter in your name in a drawing to win a $25 Amazon gift card. Just something fun to do. And again, we really want to make sure that these future webinars that we do are as most value to the people that attend. And just a little bit about Veolia Water Technologies. We're a leading water and wastewater treatment company. We're globally located, of course, and then we support our customers through providing project support, technologies, and of course, a wide range of services that support both the projects and technologies that we install. And then all of our activities we offer is, of course, municipal, which we're talking a little bit about today, but we work in a variety of industrial markets as well. And now we'll transition to the technical portion of our presentation. We're lucky to have two panelists here with us today. The person that you'll be hearing from first, Miriam De Laurenti Noel. A little bit about Miriam is that she graduated in geological engineering from Polytechnique in Montreal in 2010, and she's been working for Veolia since that time. And she works in piloting, R&D, development, laboratory studies, and process engineering. And currently, as a process engineer, she has the opportunity to use her competencies and field experience in water treatment by designing water treatment chains for the heavy industry, aiming to reach over stricter environmental compliance. And also with us here today is Daniel Lamar. He's been working as a process engineer for the last 20 years for Veolia Water Technologies based in Montreal. And this brought him to work on both drinking water and mainly wastewater treatment for both muni and industrial projects. His position brings him to work on R&D activities, the introduction of new technologies in the market, process engineering on full-scale projects as well. So he'll be joining us a little bit later, maybe for the question and answer portion. But at this time, I'd like to hand the webinar over to Miriam, who will share a little bit more about this technology. Miriam.
Thank you, TJ. So good afternoon, everyone. Thanks for joining us today for this presentation about the Biostyr application. So today, what's the agenda? It's first a presentation of what's the Biostyr technology for those of you who are less accustomed to heard about the Biostyr. We will also talk about the Biostyr DUO, which is the process intensification version of the Biostyr, the classical Biostyr. And we'll do some comparison with secondary treatment options, and we will present star case studies about the Biostyr just to show various things we will highlight through the presentation. And at the end, there will be some question if there is anything you would like to know more about the Biostyr applications. So first, what's the Biostyr? A Biostyr is a biological aerated filter. It's based on two water principles. It's a biological treatment. It can be both aerobic or anoxic. It uses a fixed biofilm. And it's also a physical treatment by granular filtration. So the media used in the Biostyr can do both filtrations, and it's a support for the biomass to grow up. This is a general arrangement of a Biostyr and a Biostyr DUO cell. So the wastewater is either fed through an effluent channel, or it can be pumped as well for a smaller application. It goes to the bottom of the cells. From there, the water goes up through the filter. There's the media floating there. There's a nozzle deck, which is the media retention systems, and then the water goes to the top of the cells, where it flows back to an effluent channel. So now, how does it work? When the Biostyr is in operation, this is a gravity flow. So the water goes down, the flow goes down in the bottom of the cells. The water goes up through the cell. As I mentioned earlier. And there's also air grids right here, you can see, that will get the air for the biological treatment up in the media. If there's some anoxic, well, if the Biostyr is anoxic, there will not be air, there will be no aeration. And if there's simultaneously anoxic and aerobic zones, the air grids will not be at the bottom, but will be higher up in the filter. So when it's filtrating, the water goes up, the air goes up, and it excites the cells to the effluent channel. So the main advantages of this flow is the filtered water is exposed to the atmosphere, so there's no odor related to the water treatment because you are in contact with clean water instead of the raw water. And there's little pumping required, since the only pumping required is to get the flow down the cell. Sorry, but once the water is down, it's all gravitary flow. Now, when the cell is in backwash, there's a common pool where the effluent goes. The water for the backwash comes from this common effluent channel. So during backwash, the effluent valve closes. The water from the pool goes down. There's still air used during the backwash to make sure that the media is well scoured, to make sure we remove everything we need to remove from the filter. Dirty water goes down, and then it goes through a main header where all the backwash water goes to go in a big backwash storage tank to be released upstream or to be treated elsewhere, but this is something separate, sorry. So the advantages for this type of backwashing is there's no clean water storage tank required, and there's no backwash pump required. The only backwash pumps required is for the management of the dirty water, but dirty water is accumulated through a tank, so the flow rate required is smaller because you just release the water slowly through the system instead of all at once. This is to illustrate how the effluent from all the cells go to the cell in backwash, and then the dirty water is collected and go to a backwash storage tank. Now we look at the component of the Biostyr cells. First, one of the main item of the Biostyr cell is its media. It's biostyrene. So this is small beads that will float. They are really light. They're resistant to abrasion and chemically inert, so there's no need to replacement. These are in the cells, and you don't need to replace them over time because they are typically not moving. Then this is the inside of a cell. This is what you'll see if you look inside the cell. There's the trench covers where the water goes in the cell and where the water excites during backwashes. The air grids, which are stainless steel pieces where the air will go out from there. And then you can see up is the nozzle deck where the water excites, and there's a, yeah, this is where the clean water goes out. So the particularity, I will talk a little bit about Biostyr DUO. We will concentrate on Biostyr DUO later on, but one of the particularities for the Biostyr DUO is the need of trench covers on the floor. So you make sure that the K5 media does not go through in the influent channel. So you can see here representation of the trench cover itself with little K5 MBBR media chips that could not go through. So they are kept inside the cells and then there's no media loss. So now this is the filter gallery of a Biostyr wastewater treatment plant. So what you can see on the left and on the right are the Biostyr cells. You can see in the middle, it's the backwash main header. This is where the backwash water is collected to go in the backwash tank. The backwash balls that allow the backwash are below the grates here. And there's a piping allowing the wastewater to go at the bottom of the cells. You can also see the air header at the top here. The air all goes to this main pipe and goes to each of the cells. Now, this is a look of the nozzle deck. So we've seen inside the cell. This is outside of the cells. When you look on from the top of the cells, so you can see all the little nozzles on the nozzle deck. What you need to know is the nozzle deck is prefab nozzle deck slabs. So these comes all fabricated and they're just installed on site. And you can see where the nozzles are installed one by one after they are installed from the top. So it's easy to install. And this is the look of the nozzle deck, the nozzles that keep the biostyrene beads inside the cells. So now this is a quick overview again of the cells, which what I want to show you here is the gates that allows the clean water to go out of the cells. When there's some maintenance required on the nozzle deck, these gates are lowered, so there's no water coming in, so you can go down here to do maintenance when required. This is not something need on regular basis, but sometimes you may want to see what's you may want to go down to see how the nozzle deck is doing. So this is how you can do it. You lower these gates and you have access to the nozzle deck for maintenance. And you can see a test in clean water right here. So this is what a Biostyr cell looks like during a, well, not regular operation, but during a operation with aeration. This is an operation. What I want to highlight here is that it's fully aerated effluent. The air, there's a strong aeration. This is because this is a very compact system. So the aeration requirements are the same as a regular biological treatment, but since it's so compact, it gives an impression of very high aeration. And you can see that it's an even flow distribution because you can see it's all evenly distributed everywhere through the cell. Biostyr and Biostyr DUO, they can be operated in winter, even if it's an outside application. So you can see here with the snow. Now, one of the things with the Biostyr and Biostyr DUO operation is that it's fully automated technology. So the number of cells infiltrations are controlled by the automation. You can decide to control them however you want, but by default, the number of cell infiltration is according to the hydraulic load and the pollutant load. What you need to know is the cell goes in idle by itself and go back to filtration according to the requirement of the cells. The main objective here is to make sure that the biomass is staying in the perfect conditions to thrive and to make sure they're never starved or anything. So this is why there's idle cells, to make sure that the biological of the cell is always optimal in all conditions. Backwashes are based on time or head loss, so it's automatic as well. And the aeration rates is also controlled by the automat to make sure that you have the right amount of air for the bacteria, especially for the nitrification, to make sure the nitrification are according to the requirements. So there's more air when there's more ammonia and less air when there's less ammonia. So it's efficient, and it allows good water quality at the end. One of the good thing about the Biostyr is with one single filter, one single cells, there's a lot of possibility for the design. You can design a Biostyr for carbon removal, for nitrification, denitrification, before or pre-denitrification or post-nitrification. You can do carbon removal and nitrogen within the same cells because the Biostyr allows biomass to grow for carbon removal on the lower portion of the biofilter, and then nitrification in the highest Bs. It's also possible in one single stage to add pre-denitrification by recirculating the effluent charge with NO3. So you have an anixic zone at the bottom of the cells that will allow the denitrification, and then you'll have aeration to get to the nitrification and or carbon removal. Now you may wonder what's the possibility for the treatment of a Biostyr. How low can it go? One thing to keep in mind is the design of each Biostyr is according to what's the requirement for the discharge. So if you need 5 milligrams per liter as total ammonia, well, it won't be designed for below 1. It's going to be designed for 5, but it's just to give a general idea of what's the possibilities, how low you can get with one single Biostyr cell. One thing I want to highlight here is phosphorus removal is not achieved. There's no biological phosphorus removal with the Biostyr. However, it's possible to get Biostyr with an active flow downstream or any ballasted flocculation for chemical precipitation of the phosphorus. And with this combination of Biostyr and ballasted flocculation, it's possible to go below 0.1 milligrams per liter as phosphorus. It's just something you need to keep in mind. So what are the highlights of the Biostyr process? Something I will repeat often during the presentation. This is something that is very compact. Very compact also means it reduces the construction cost because you will need less drilling, less concrete, less blasting, so it's easier to for the construction of the process. It's also very easy to operate. It's fully automated. There's little to no operator intervention. You still need someone to look for optimization of the process, but there's a lot of alarms and there's a lot of things in the operation of a Biostyr that makes it quite independent when need be. And there's no concern with sludge settling or bulking, since it's a fixed film. The backwash are optimized to make sure that the sludge are managed correctly and the biomass is correctly managed. So where does a Biostyr really shine when you look at different technologies? It's when you have a footprint constraint site. So when you have a very limited space for expansion, when it's very costly to expand, as an example on the right side, there was a hill on the site, which would have been really costly to just blast through it. But using the Biostyr, you didn't have to blast the hill, so it was interesting as for construction cost itself. This is an application that is really interesting when there's an existing primary clarification, because it do require primary clarification upstream. It's a filter. It's a process that is really good for large flow. When the flow is higher than 25 million liter per day, and there's no limitation as a max flow. It's just a question of number of cells. I'm so sorry, I'm sick. So it's also a good project when there's some nitrification required, because the Biostyr can do BOD and nitrification removal in one single cell. So it's there's only one need of one step. You don't need 2 steps to do both. And it's an energy efficient technology. I will talk a little bit more about this one later on. So Biostyr. You might have heard that there's some people that are concerned about losing some media during backwashes in the backwash tanks, and then getting the beads out of the backwash tanks is not an easy task. Most of the time, this is, well, most of the time this is due to a bacterial stress. What could cause a bacterial stress? One of the causes we've seen often is the lack of phosphorus. There's not enough phosphorus in the biostyr. What's the results is the bacteria as stress. They are creating exopolymers, and these exopolymers will create clumps of biostyrens that will be dragged through the backwash. So there's a couple of solution mitigation. It can be either to control the process so there's no bacterial stress, which is really hard. Another solution was to install a big trap that will allow the bees to be trapped and then sent back into the biostyr cells. It worked really well. And the third one is the Biostyr DUO. So the process intensification is also a mitigation of the bead loss. So how can a Biostyr DUO eliminate the bead loss? I will go very briefly here because we're not, I will present the Biostyr DUO soon. What you need to know is Biostyr DUO is for 2 different media used within the Biostyr cells. One is the Biostyr, which is the same one from the classical one, and the second one is the MBBR. So in the happen is the MBBR acts as a filter to make sure that the biostyrene beads cannot pass through and cannot be lost during backwashes. The clumps just get stopped by the MBBRs that are floating around. This has been proven for all the DUO application, which includes the Binghamton one, which is located in US. It is a Biostyr DUO cells, and it's also been proven in Cataraqui Bay. Both of these plants have been operating for a couple of years now, and none have seen any media loss since their startup. So now it leads up to what is a Biostyr DUO? Biostyr DUO is a biostyr in which you're adding MBBR. So it's like having a small MBBR tanks upstream of your biostyr, but the MBBR is in fact inside the biostyr cell. It could do some BOD removal upstream of nitrogen removal, or it can be the annexic part during the pre-denitrification upstream of a carbon nitrification removal. So this is, as I mentioned before, the BAF version of process intensification. The objective is we have a known volume. How can we do more within the same volume? In a biostyr, there's an empty space for bead expansions. This empty space for the Biostyr DUO is used as an MBBR tank. So we're adding MBBR carriers in the empty space right here to provide the MBBR portion of the Biostyr DUO. It adds more biomass, so it can allow more treatment, more pollutant load treated within the same cells because you're using the MBBR, which was not there before. So one of the questions you might ask yourself is, how does the MBBR carriers are actually reacting with the biostyrene? The good thing is the density between both of those media is very different. So the biostyrene floats and the MBBR just rolls around below the beads. And you have 2 pictures here, one from a pilot with clean water and one with a pilot that's been used for a couple of months, probably more than 1 year. You can see a couple of beads being stuck here and here, which show that the 2 media are in relation one with another. So there are some beads that might get stuck at some point when we go really aggressive on the backwashes. But the good thing is these beads are not progressing. There's not more and more beads. It's pretty stable over time, and it's not having any impact on the process efficiency. Why go with the Biostyr DUO? Well, we observe longer filtration times. This is mostly due because the MBBR carriers are below the cells. And in the Biostyr cell, most of the heterotrophs removing the COD and removing the NO3, they grow on the lower parts of the Biostyr. But with the Biostyr DUO, they actually grow on the MBBR carriers. So these heterotrophs doesn't grow on the biostyrene media. It's easier to scour with the MBBR carriers, and it decreases the head losses in the actual filters because these very bulky bacteria are in the MBBR where there's no effect of clogging. And the Biostyr really sees the autotroph bacteria which are less clogging. It also allows to have a more compact system because you have the MBBR taking care of part of the load, so you can have smaller treatment for the Biostyr. And as mentioned before, it prevents the Biostyr media to be lost during the backwashes. So now a comparison with other secondary treatment options. This is a big table. We'll go with the highlights. So we're comparing the conventional activated sludge with Biostyr and Biostyr DUO. In all cases, this is biological treatment requiring primary treatment. One of the big advantages of the Biostyr is it can take a higher hydraulic design flow. With the activated sludge, we talk about 2 times the average daily flow. With a Biostyr, we can go up to 3 to 4 times. This is going with the diluted wastewater. It's hard with an activated sludge to have a diluted wastewater because it's complicated to manage your MLS. With the Biostyr, it's not a concern because the bacteria are all fixed on the media, so they're not washed away. They just stay on the media. There's a sludge bulking that is often a problem with the activated sludge when there's an issue with the biology in the activated sludge. This is not an issue with the BAF because the backwashes controls the sludge. It controls the biomass being released. So there's no accumulation, and it really reduces the risk of having trouble with sludge bulking. Another thing is the biogas generation potential of the sludge from the secondary treatment. For the activated sludge, the biogas generation is low because the age of the sludge is high, so there's some hydrolysis of the sludge already in the process, which release the methanogenous potential. In the BAF, this potential is very high because the sludge is very young, so you get all your methanogen potential right here. Footprints, once again, we already mentioned, footprint is lower with a BAF considerably. One thing is there's no possibility to do biophosphorus removal with the BAF, which is possible with the activated sludge. However, you can always think about tertiary treatment to remove the phosphorus using chemical treatment like ballast flocculation, which is very small as well and easy to operate. So estimated footprint, Biostyr is way smaller than other technologies. Let's forget about the first one because it's BioP. So let's compare the activated sludge chemical with the Biostyr. There's more than 50% reduction of the space. This is a footprint comparison with the aerobic granular sludge. So the Biostyr is way smaller than the aerobic granular sludge. Once again, you might need to add a little footprint for the ballasted flocculation for P removal, which is removed with the AGS, but it will still be smaller than using Biostyr plus ActiFlow will be smaller than using AGS. So now let's go through some case studies. Now that you know what's a Biostyr, let's go to see how it performs in the real world. So Biostyr over the world, at the moment, there's over 180 references over the world. As you can see, we are starting since 2018 to see the first DUO applications. This is a fairly new process, so this is why there's not so much references, but it's going to grow eventually. All over the world, we're talking over 20 references in North America, and there's a lot all over the world. So now we selected a couple of them that were specific for various things we already highlight through the presentation. So we will present them here just to have a more visual impact of what was discussed during the first part of the presentation. So the first one is the Portsmouth Biostyr, which is in the USA. One of the specific of this project is the very limited footprint. This is a plant that was only primary enhanced chemical treatment that was working well for what it was doing, but at some point they needed to do complete nitrogen removal. So they needed to increase the capacity. Well, they needed to change the process to allow nitrogen removal. But they were very, very limited in the footprint. It's on an island. There's a lot of parks, historical districts, and everything around. So they were very, very tight to do some biological treatments, secondary biological treatments. They did several pilot studies. They tested MBBR, biomag, biostyrs, and doing an analysis of the three technologies, they decided to go with the biostyr. So this is where it's getting interesting. The plant before was the enhanced primary here. What you can see on the right side is the new plant with total nitrogen removal. So there's biostyr cells right here on the left side of the right picture showing the nitrogen removal, the nitrification removal biostyr followed by the denitrification removal biostyrs. And as we can also see, the average flow from the primary clarification plant to the Biostyr BAF plant, there's an increase in the design flow. Here are a couple of results from the plant. So what you can see is TSS removal, BOD removal, and total nitrogen removal. This is the load going to the environment. What you can see is when the plant with the biostyr went online, there was a drastic drop of the TSS and BOD removal. Total nitrogen followed shortly after, just the time the nitrification and denitrification bacteria just started to be working in the process, since you need to acclimate your bacteria. So you can see a very good performances until, since the startup of the plant, actually. The second case study is Onondaga in Syracuse, USA. So one of the specific of this project is they already have activated sludge for secondary treatment, but they needed additional nitrification as a tertiary treatment, and they needed to have some phosphorus removal as well. So this case study is selected because you have a biostyr for nitrification followed by active flow for phosphorus removal. This is what we can observe for the nitrification performances. So performances of the secondary treatment is on the left side of the graphs, and then on the right side, this is when the biostyr was in operation. And what can be seen on the side of metropolitan Syracuse is that the BAF process lower ammonia down below 1 milligrams per liter at all time. And then for the active flow performances, they needed to have a very stringent phosphorus removal. So what was observed since the beginning of this plant is a total phosphorus from 0.05 to 0.08 over several years. So below the 0.1, they needed to make sure to meet. So biostyr and active flow is a very good combination to achieve a low final effluent phosphorus concentration. The third case study selected is Cagnes-sur-Mer, which is in France. This one is selected because the speed flow is a DAF. So this dissolved aeration filtrator. This is used as a primary clarification step. And then the Biostyr is downstream of the speed flow. As you can see, once again, footprint was very, very limited for this plant. This is a picture they sent me, an aerial version of the plant. The plant. It's stuck between highways. Another thing, this is a Biostyr DUO. This is one of the Biostyr DUO for carbon removal. So water quality through the treatment chain. So since it's for carbon removal, it's COD TSS removal. You can see a good performances for both the speed flow in red and the Biostyr in yellow that meet the criteria for TSS and for COD. And since it's a speed flow, we also wanted to see the performances of the sludge. We could see that they manage about 60 grams per liter sludge for the operation of their speed flow, which is very good because it diminished the handling of the sludge. It's easier to manage on sites. So that was a very good combination with limited, there are still chemical involved, but limited chemical requirements. The second case study, we don't have results yet because the site is still in commissioning. It's Mar Naval. One of the particularities of this project is it was a classical Biostyr for denitrification, nitrification, what is called NDN. They had classical Biostyr and they decided to switch them all to Biostyr DUO. So right now what they're doing is they are getting the last Biostyr cells down to DUO cells. So since I don't have results, I will present how they did the commission. Well, how they did the switch from the classic to the DUO. So they had to install some trench covers to make sure the K5 stays within the cells. So this is the trench cover themselves. They had to add some MBBR media during the process because they just had the biostyrins within the cells. So the MBBR media was installed through the nozzle deck in the port for that. Sorry. And what are the takeaways so far during the commissioning is they have 40% less dirty water, backwash water, because they have less clogging, so they do require less backwash cycles. So they reduce the amount of water produced and to be treated at some point. And they also increase the efficiency of the nutrients removal because reducing the clogging to the cell reduces the bypass they needed to do at some point when there was too much load. They had to bypass part of the flow from the Biostyr. And since they switched to Biostyr DUO, these bypass events were very, well, they were less frequent because the clogging was well managed with the Biostyr DUO. And then there's Owen Sound in Canada. This one is mainly to show you the importance of, well, this is a diluted application and there's a big peak flow factor in this one. It was designed for a peak flow of 3.5, the average design flow, which is about 87 million liter per day. And what we wanted to show you right here is, well, sometimes you design peak flow, but you don't really know what's the real performances of the filter over time. In this particular case, if you look at the left side, since 2017, the peak flow was achieved and even exceeded through the plant. And there was no issue with the operation of the plant, no bypass, and all was working very well with the Biostyrs in Owen Sound, even if we went to the peak flow. Now, as a lot of technologies, Biostyr, well, you like to put your hand in it and everything. So there's some piloting. We mentioned piloting for one of the plants that they tested several technologies. Do know that Veolia has pilots to test the Biostyr, both Kruger in the US and Canada. We both have pilots that it's 36 inches columns that you need to feed them with primary effluent from 2 to 8 cubic meter per hour. A pilot test is about 6 months. It can handle various configuration. This is designed so you can move the air grid inside. You can test DUO, classical, with denitrification, with or without denitrification, nitrification, whichever what is required on site. And the main objective when we're doing piloting of the Biostyr and the Biostyr DUO, it's to demonstrate the performances of the process. It's to the results helps to optimize the full-scale design, because the design is done on hypotheses that are usually applicable, but when you actually tested it beforehand, you can be more aggressive in the design because you know exactly where you're going. And one of the big highlights of piloting that we need to really stress here is the operator gets to know the technologies. So the operators can play with the pilot, they can work with it, they work with the people, and they have people coming for training and to follow the pilot, so they can really play with the thing before going large scale. So it's really helpful when you go with commissioning and everything. You have the knowledge already in your hand when you start the pilot, when you start the full scale application. So now, what are the key takeaways about Biostyr? When do you need to, well, when should you consider Biostyr or Biostyr DUO process? Is, well, when you need a process and operation simplicity, there's not a lot of mechanical equipment, there's a lot of automation, so it's really a process that is easy and simple to operate. There's a good health and working conditions because it's an upflow, so you're always with the clean water. You're on the clean water side, so this is better for when you have an outside treatment. It smell nice. It looks good because it's clean water. It's a very, very good application when you're landlocked, when you don't have any expansion possibilities, because you have houses around, when you have water, when you're on an island, or when the land is hard to work with, when there's hills, a lot of rocks. So this is a good application because the footprint is so limited that you have less problem handling the space limitations. And since it's a very the footprint is very limited, the capacities of the treatment is very high, and it works really good in the diluted water. So that concludes the presentation. I hope you enjoy. And now, TJ, I'll let it to you for the questions.
Great job, Miriam. Thank you so much for sharing all of that very informative information and case studies about the Biostyr and Biostyr DUO. I just want to remind everyone, on the right side of your screen, you should see that question panel. If you have a question and you haven't had a chance to go ahead and enter it, feel free to do so now. We have a couple questions that were entered throughout the presentation that we'll start answering here in a moment. But we'll, for the next so many minutes, we'll try to get to as many as possible. If there's a question that comes after the webinar, or you have a question tomorrow, there's an email address on the screen now, water.info@veolia.com. Go ahead and write that down, and if you send an email to that, we'll make sure you get to the appropriate person for follow-up. So just to start with the question here, one question that we have is what is the head differential required across the Biostyr tank? Between Miriam and Danielle, I don't know who should take that particular question.
I can take that one. The head loss, total head loss over the whole process is about 3.5 to 4 meters. The pressure differential through the media itself is limited to 2.5 meter. So you would normally basically backwash when you hit 2.5 meter of head loss, but you also have some head loss on the feed distribution system and on the back end on the treated effluent overflow air. So we say usually typically about 3.5 to 4 meters.
Great, thank you for that. Just another question. Quite a few are coming in a little bit, so we might be jumping around a little bit, but can you compare a little bit about the air requirements, or the air that's needed between conventional activated sludge and the Biostyr DUO?
Yeah, first off, the oxygen requirement AOR will be lower with the BAF because of the limited hydrolysis of the incoming solids. So in your activated sludge system, the TSS remain in the system for days, equal to the SRT of the system. While for the BAF system, the Biostyr, this incoming solids are physically filtered out, and a typical filtration cycle will last somewhere between 24 to 48 hours. So the solids in the filter will have somewhere between 24 to maximum 48 hours for hydrolysis. So hydrolysis is very limited in the Biostyr. So that lowers the oxygen requirement. And then the second part of the answer is the high oxygen transfer efficiency of the Biostyr. So you notice that the air grid is located at the bottom of the filter. So the air bubble will be diffused about 6 meters lower than the nozzle deck, and then the bubbles will go upward, and then they will hit the K5 media, the MBBR media, and that media will basically break these air bubbles into smaller pieces, and then the air bubbles will eventually hit the biostyrene media, and this media acts as packing, similar to the packing, inert packing you have in typical columns in chemical engineering. So the packing will increase the retention time of the gas bubbles in the filter, and that will increase the oxygen transfer. So at the end of the day, even if the air diffusion system is on coarse bubble aeration, the oxygen transfer efficiency turns out to be significantly higher than the typical fine bubble aeration systems. So at the end of the day, the total horsepower requirement for the aeration system is significantly lower than a conventional activated sludge system.
Okay, great. Thanks, Daniel. A question, actually quite a few questions are very similar here. So it's sort of a two-part question. Can you first talk about the solids in terms of the influent or the pretreatment needed to handle solids before it gets into the Biostyr? And then a follow-up to that is, what do you do with the solids that are in the backwash of this particular system? So can you handle that for us?
Yep. Okay. So at the upstream of the filter, the requirements are a primary clarifier. Not that solids themselves in terms of concentrations are so much of an issue, especially for diluted water. But experience showed that if you don't have this primary clarifier, you'll end up with surface clogging of the filtration bed. And that's probably linked with probably toilet paper and fibers from the wastewater. So the primary clarifier will remove these fibrous material that will and allow the TSS to penetrate deeper in the bed, in the media filtration bed. And then upstream from the primary clarifier, you need we will require, depending on which Biostyr configuration, if you use a classic Biostyr system without the MBBR media, we only need a 1/2-inch bar screen. But then if you use the Biostyr DUO, which is basically what we propose all the time now, we will ask for 6mm perforated plate screening. As for the backwash wastewater residual, this water goes to equalization tanks that are designed usually to handle at least more than one backwash, full backwash, so usually 2 full backwash, to provide more flexibility for operation. And then the backwash wastewater will be pumped to treatment. So treatment meaning clarification. The treatment could be 2 options. Either the backwash wastewater is returned to primary clarification or co-clarification, or it could be sent to a dedicated clarifier or DAF system. So the two options are possible one way or another. Even if it goes to a dedicated clarification system, the effluent from that clarifier or DAF system will go back to the Biostyr influent. And in terms of volumes, how much backwash wastewater is generated, rule of thumb is somewhere between 10 to 15% of the incoming flow. Of course, this is very site specific or project specific, depending on the applications. If you're running with, if you're doing tertiary nitrification as an example, you'll do much less backwashes because there's much less solids reaching the BAF. So this number will be lower, and to the other end, if you're running with a high BOD load, then you'll do more backwashes, so the percent of backwash wastewater will be higher. But rule of thumb, 10 to 15%.
And then just a follow-up on that, what is the sort of the concentration of solids within that backwash stream? I know it probably varies quite a bit, but do you have any feedback on that?
Yes, actually it doesn't vary that much because once the filter is reached the maximum head loss and is ready to be backwashed, the mass of solids that's held in the filter belt is relatively constant. So the backwash wastewater concentration is usually relatively constant. I would say somewhere between 500 to 1,000 milligrams per liter.
Great, thanks. Interesting question here is how does this system work with in a municipal setting with, say, high loading events, or on the inverse of that, if there's a large like rain event and you have increased flows? Can you talk about how the system reacts to those two scenarios?
Yeah, in terms of increased flow, so let's say rain event, snow melt conditions, the system will simply do nothing. It will just keep remain in filtration with all cells in operation, and the flow will just reach, will be higher, velocity will increase, but that's it. The control system will just continue managing the aeration system and managing the backwash once the filter gets to the filter backwash threshold. So nothing will happen on the BAF operation side. I can add that if the influent flow reaches a value that's beyond what the filters can handle, so if you're past the hydraulic capacity of the filter, there are some influent overflow areas built in the influent flow distribution channel, and the influent will simply overflow to the effluent channel that's located just underneath. So in terms of handling the flow, the Biostyr construction will handle the flow with as much volume, as much flow going through the BAF, typically up to 3 to 4 times ADF, and anything beyond that will simply bypass directly from influent channel to effluent channel. On the other end of the spectrum, when you're running at low to very low flow conditions, there's no real issue either. The only thing is we want to ensure we keep a minimum velocity so filtration velocity through the filters to make sure that we have even flow distribution. When we reach a lower limit, we may not end up with a very good flow distribution, and we could have more biomass growth and more clogging in certain areas of the filter, and that's something we want to avoid. So the control system will, in this condition, put some filters, some cells into standby mode, and the operation will be done with fewer cells in operation until the flow resumes to higher flows.
Great, thanks. Another question that came in that's interesting is it's about the media for the DUO. And you talked about using the NX Colonists K5 media, but is there any studies or use for using an alternative media like the NX Colonists Z MBBR instead for that particular media choice?
So far, all studies were limited to the K5 media. The objective of that media is to provide biofilm surface. The K5 offers quite a lot of surface with a specific area, protected area of 800 square meter per meter cubes. And at the same time, we want a media that is somehow porous, so which has openings allowing water to flow through the media. So if we were to use another type of media that is not an open, as an example, the Z media, again from an NX Colonists, which is like a Pringle chip, similar to a Pringle chip, doesn't allow water to flow through. And that could cause some problems, especially during backwash condition, where you want the water to flow at high velocity downwards during backwash operation. So far, yes, we're limited to the K5 media.
Okay. Another interesting question it has to do with nitrification. And has there been any analysis related to N2O emissions that can result in nitrification systems?
There were some studies done a few years ago, and I know the techniques used for measuring N2O have evolved tremendously in the last few years. So new studies would be required to have much more precise numbers on N2O emissions. So the first preliminary numbers we could measure a few years ago were that these emissions were somehow similar to an activated sludge system. But we could see some spikes in N2O generation being emitted right after backwash. So there is some stress for sure applied on the nitrifiers during backwash. The filters has probably less aeration, and they are physically shaken. And you could measure some N2O spikes for just a few minutes, but and there's probably something to investigate there. And I know there were some pilots done to try to mitigate N2O emissions, especially concentrating on these periods right after backwash. But as a general question, so similar to activated sludge.
A question here is you talked a little bit about doing tertiary treatment to do some P removal, but has there been any kind of pilot test or study on adding dosing coagulant in the cells to go ahead and do that in sort of a true all-in-one solution with the Biostyr?
Some studies were done, but at the end of the day, dosing coagulant directly in the BAF turns out to be unproductive to some extent, meaning that if you want to reach very low final effluent TP, you will need to dose quite a lot of coagulant upstream from the filter or at the filter inlet, which means that in the upper part of the filtration bed, the dissolved phosphorus concentration, so ortho-P, will be at very, very low concentrations, and you'll automatically be in a phosphorus limiting condition. And that's not good. That leads to well, what Miriam was mentioning earlier with the exopolymer excretion and bad performance of the BAF. And if you are not looking for these very low effluent TP concentrations, then the solution is to dose coagulant in the primary clarifier. So we have plants in operation where the final effluent TP concentration is less than 0.5 milligrams per liter, with just a primary CEPT with Biostyr, and these plants run without much issues. It does require a regular measurement of coagulant dosage, of effluent, ortho-P, to make sure that you're not under P limitations, but it's doable down to 0.5. But then if you want to go to less than 0.5, the solution is really tertiary treatment.
Great. Well, it looks like we are just about out of time for today's webinar. I want to thank all the people that attended this webinar and submitted questions. It was a great interactive session. In addition to that, I want to thank both of our presenters. First off, Miriam, who did a great job presenting the Biostyr and Biostyr DUO, as well as Daniel Lamar for helping out on the technical questions that were asked. If we didn't get to your question, please feel free to follow up on that email, water.info@veolia.com. And lastly, just if you can, remember to take that survey at the end of the presentation, and we'll be sure to enter you in for that drawing. So at this time, thank you all for your participation, and look forward to seeing you on a future webinar. Take care.